Matthew is a senior student at Stevens Institute of Technology, currently pursuing an undergraduate degree in biomedical engineering with a major in software engineering. Oh, and a major in software engineering. Their research focuses on biomechanics, 3D modeling, data science, and medical devices. So please take it away.
Great, thank you so much for that introduction. So again, my name is Matthew Feroz. This is my research, the biomechanical implications of the heel hook submission, a comparative analysis across age and gender in jiu-jitsu practitioners. So to start off, what exactly is jiu-jitsu and why is it important to me? Why did I do research about it? Essentially, jiu-jitsu is a martial art that focuses on ground combat and submission grappling, and using leverage, joint locks, holds, and submissions, you're able to submit your opponent and almost like compete in a martial arts setting without actually hurting your opponent. So me over there in the blonde hair a couple of years ago, I had been training jiu-jitsu for about 2 to 3 years. It's like a part of my life that I really enjoyed. And as a biomedical engineer, I'm always asking myself questions about how can I use the things that I learned in class, the concepts and understandings that I have from jiu-jitsu, and how can I combine them? And the way that I found that would be most effective was in my biomechanics class, creating and utilizing the technology and knowledge that I learned in there to do research. So essentially there's a problem in jiu-jitsu, and that's the heel hook. What it is a move that places excessive force on the knee ligaments by twisting the heel while having the hip and leg completely locked. So as you can see, this practitioner right here is applying the inside heel hook technique to his opponent. The man on the right is twisting the heel of his opponent so that all the forces are translated straight up directly into this knee. The problem with this is that although jiu-jitsu allows these moves and it's a submission grappling sport, injuries occur often. And injuries occur often for people who are younger practitioners, older practitioners, and people who may not want to be injured or may not want to compete at that level. So this is like a reason why there's a lot of injuries, or specifically knee injuries in jiu-jitsu. You'll see that most jiu-jitsu practitioners are always complaining about their knees, especially me. And as somebody like who sees that, I obviously want to fix it and then make it better for the people who practice jiu-jitsu just as well as me. So essentially, how does the injury occur? During a heel hook, you're essentially making a movement that would usually occur in like a high speed like turn, or like in another sport, let's say you're playing soccer, you turn too quickly and you feel your ACL tear. That's not exactly what happens in jiu-jitsu. You're holding your opponent in an isolated position where you are applying that rotational force to that leg. And what occurs is people won't understand how to escape it, or they'll think that they can last longer in the submission that they can, and then they end up tearing that part of their leg. It's a really brutal submission, but it's very effective because of that. And there's been a huge resurgence of it in the most recent years because of this. So understanding a little bit more about the knee and what exactly I'm trying to model in my 3D model later down the line, essentially the three things that I wanted to identify and understand the most were the LCL, ACL, and MCL. And you'll notice that these specific tendons lack antagonistic muscles that almost make it so that when you're applying the force of the heel hook onto that knee, there's not going to be a muscle that you can train in order to really make it so that that tendon is more protected. It's more like you have to train the surrounding muscles around it in order to make it stronger, which is not a problem. It's just a part of anatomy, and that's why that move is so effective. So again, I've created a model based off of this, and I wanted to make it so that the model contained each of the factors affecting the tendon strength within the body. So to do that, I'd first create a model. This is a model that I found online. Essentially, it's just the femur, the tibia, and the fibula. And essentially what I had to do was recreate this model to fit my purposes for a biomechanical test and demonstration. So in order to collect the data, I first had to find all of the information about the tensile strength and the mechanical strength of different tissues throughout different practitioners. So the three different practitioners I decided were male, female, and pediatric, because all three of those people do jiu-jitsu. And you'll see that it's mostly prevalent in male practitioners. Like jiu-jitsu is mostly male-dominated sport, but there definitely are a lot of female and pediatric practitioners as well. So essentially, looking through a bunch of different data and a bunch of different research papers, I collected information that I would be able to utilize inside my model. For pediatric, it was actually quite easy to find. Most of this data is from cadavers. So for pediatric, I didn't really have that big of a pool, but for the male and female, I was able to find a little bit more. It was just difficult finding people in the age range of most practitioners. So most practitioners of jiu-jitsu are 20 to 40 years old, but most of these patients were around 80 to 70 years old, which is understandable. But the data still showed trends, which is the most important part. So going into my model, essentially what I had to do was recreate a model that would simulate the exact force being placed onto an opponent's leg as if it was like an actual limb. So I first started with modeling the bone structure of the actual leg, but I wanted to include there at the bottom a pin that would absorb the force of like rotation and would translate up the entirety of the leg into these different tendons. So as you can see, the LCL, ACL, and MCL, they're all different colors. Those all have different mechanical and tensile properties actually linked within them. So I essentially placed a 10 Newton, 50 Newton, and 100 Newton force onto that little pin at the bottom in order to make sure that that force translated up to the top or up into the knee. And so that I could see which part of the knee was most effective and which part of like the tendon strength which tendon specifically should you increase the most, or strength should you increase the most in order to protect yourself more from this emission. So looking at the actual test analysis, looking at 10 Newton, 50 Newton, and 100 Newton forces placed upon the knee, you can see that the LCL was one of the ones that really took the most amount of stress. You can see the picture, the red indicates where the most amount of stress is. And then usually in terms of the Newtons that I used for this actual report, it's kind of hard to determine how much force you're placing torsionally on a heel hook because it usually isn't like, oh, I put a little bit of force or I put 1 Newton of force into a turn. You're usually turning with your entire body. It's like a very complex position. So I just thought that 10 Newtons, 50 Newtons, and 100 Newtons would kind of simplify it the most. I found that it really doesn't take a lot to tear your ACL or all your ligaments in your knee, which is kind of scary, but it's also important to understand. So this is the pediatric data, and then this is a comparison of all of them. Looking at the graphical analysis of this data, you can see that pediatrics have the highest values for maximum stress they can absorb, the minimum factor of safety, and the maximum strain. So this factor isn't exactly a good thing because imagine that you're a practitioner who is extremely flexible and can really take these submissions and grind them out and have more time to escape, essentially. That isn't exactly a good thing because that injury is going to be way more catastrophic at that point. So you are essentially giving yourself a false sense of security with the amount of flexibility that you have. It's almost better to experience the pain earlier, experience the tension earlier inside of your ligaments so that you'll know and understand to tap faster, and so that the entirety of the rotation doesn't like complete, and that last 1 second of time that you have to actually escape or actually like tap isn't the time that your ligament is going to snap. So it's not exactly a good thing to be more flexible, but it is important to understand that pediatrics are more flexible. And that makes sense because, puberty, they're still growing. And then you can see also that the males have are less able to absorb stress than compared to females. And that might be because females do have more laxity within their knee ligaments. You can see this in a lot of, MMA fighters and some soccer players too. But continuing onward, understanding the results is really important for a model like this. So a model is only as good as the information that you get from it. So like I said before, the LCL stands to take the most damage first, and that might be because the way that the model is rotating. So if I go back to over here, you can see that the rotation that's being placed is a outside heel hook. There's another version of this move where you can place it on the inside of the heel. That one's a little bit more catastrophic, but the outside heel hook was like one of the first to be popularized. So that's why I decided to turn with that rotation of force. Going back into where the most amount of damage is again. So the other tendons were obviously affected by this move as well. The lower portion of the MCL was one of the ones that was affected as well, pretty highly. But I feel like that might be because of the way that I modeled it. Again, this is still just a model. I wasn't able to actually model the the viscoelastic properties of the tissue within the model. I was just using, SolidWorks extrusion like parts and pieces and just connecting them to the actual bone. So it might be because of that angle right there, or it might actually be because of the tendon strength being affected. And also the ACL seemed undamaged at lower torsion. Again, this might be because of the model, but it also might be because of the like I said, direction of force that the move is being applied. So what are the next steps, and what is the understanding that we kind of gained from doing this research? So by prioritizing the improvement of strength in the ligaments on each side of the knee, there can be an increased resistance to the submission. So how do you do this? Essentially, you really can't specifically increase the strength of those tendons directly, but what you can do is do training that's kind of builds that surrounding muscle and gets you to be able to activate the muscles that need to be activated when you are being put into those positions. And that's through this thing called proprioceptive exercise. So I'm not sure if anybody's ever been to PT before, but if you have essentially any exercise that requires you to like use balance and use those small muscles within your knee or your leg to really like build that mind to like muscle connection, those type of exercises will actually help increase your resistance to LCL tears, or to ACL tears in this instance. This was research that was done on soccer players. It wasn't exactly done in contact sports. That's something that I'm still like looking for. But moving forward, the other type of way to prevent injury would be understanding and kind of having a science-based approach on how to actually defend yourself and react to this position. So I'll get into it more in this next slide. But essentially, as you can see in this little video over here, what the person in the red is doing when he is escaping the black is he is almost reversing everything that is being applied inside of the model. So you can see that he frees his knee line by pushing his other opponent's other leg away, and he allows his hips to rotate and move with the submission. So rather than having it so that the femur is locked in place, being able to spin with the rotation of torsion and being able to push yourself away from the hold is what essentially gets you out of the position. And it's really important to understand this because people who are younger practitioners or people who haven't worked with this submission before, they'll usually react by almost like pushing into the torsion. And that could cause you to almost force yourself to tear the ligament, or it cause yourself to like do the damage while you're turning. So I've seen it before where you're putting a newer person into that position and they'll react the wrong way and then they'll injure themselves. And then that's just not a good, look, and it's not, fun for the person who got injured either. So in conclusion, we need to look more into neuromuscular and proprioceptive training programs, especially within jiu-jitsu. A lot of the jiu-jitsu training isn't really standardized because different gyms have different like secret sauces, if you would call it, in terms of like training methods and what they think is best. I also think that just because this move affects more people or different groups differently, I don't think that it's a move that should be banned. Jiu-jitsu is a sport in which you're essentially signing a contract to compete in a form of competition that puts both you and your opponent at risk, but that risk is like agreed and accepted upon. And so there shouldn't be any sort of thing that blocks you from doing that as long as you're willing. And yeah, I believe that this move is very useful. And I believe that understanding the biomechanics behind a lot of jiu-jitsu moves is very important as well. As somebody who like does the sport, I am staggered. I am by the lack of research that there is in jiu-jitsu. It's essentially a biomechanic, paradise. Every single move in this has some sort of biomechanical advantage, and it's important to understand that. I'm not sure if I'm running out of time, but essentially this is my LinkedIn, and I have a works cited page over here. So thank you so much, and I hope you guys enjoy the rest of your day.
Great presentation. Thank you so much for sharing that with us. I mean, I think the most amazing thing was that you could really see your passion behind the research, being that you are a practitioner.
Yes.
So if anyone has any questions, they can put them in the chat, or you can turn your video on and you can go ahead and ask the questions. I think Franklin might have a question. Or no, sorry.
Yeah, I just wanted to make a comment. I think it's really, you made a really good point, Matt, about the lack of research that's surrounding this area. And it's really cool to see, the biomechanics and the engineering behind strategies where you can actually get out of these particular submission sites, and seeing age and sex specific differences in the amount of torsion or amount of force that can be applied. So I really like this. I just kind of wanted to get a better idea. Like, so you came up with this research on your own, and like,
Yes.
that is
Yes.
awesome. That is awesome.
Because it's a problem that affects me in the way that I don't want to compete in competitions where those moves are allowed.
Right.
So, I was like doing research one day. I'm like, okay, where does the most injuries occur in jiu-jitsu? And like, knee injuries is one of the number ones. I was like, why is it knee injuries? Oh, it's because of like moves like this. It's because of positions that put your knees into the positions like this. So it's something that inspired me. And I also want to give credit to my professor as well, Professor Sally Shady. She really inspired me to, push myself with this research. This was actually research I did throughout a class. So she, inspired me and motivated me, and I was able to produce something really great. So yeah.
Awesome.
I wanted to ask, you mentioned like flexibility. Are there any other variables or like confounding factors that you think would be really cool to put into your model? Like, if you were to continue working on this down the line.
Definitely limb length. I kind of didn't, it's a model, of course. So I needed to essentially for each model reduce the limb length for the pediatrics, the males, and the females. But we're just going to assume that a pediatric is going to have the same legs, a female and a male. So that's something that I would definitely want to do. Finding the information for like the cadavers was like kind of a difficult thing, especially for like females, because a lot of researchers, they almost don't delineate between the two when they're doing testing, which is almost frustrating because that's specifically what I want to find. So I'm hoping to look more into that and maybe recreate more models within this specific test. Creating the model and actually doing the FEA was actually like one of my most favorite parts. It's like something that I'm passionate about. I love 3D printing. I love like modeling like this. And yeah, I hope to create more solutions like this and learn more about jiu-jitsu in a biomechanical sense.
Great. And then I think the final question is, what are you interested in doing next? So in graduate school, what are the topics that are excite you as far as research? Do you want to continue in biomechanics, or are you looking for a new area?
So I think that software really is the future of biomedical engineering. And I want to create like accessible, almost open source solutions for understanding injuries and understanding where, like we don't really have access to like we have WebMD, we have ChatGPT, we can use all those things, but there's no like modeling software that I can just open up and like see, okay, I sprayed my finger this way. Is it this joint going to be hurting? Is this going to be hurting? Like software like that, empowering people to like take their healthcare into their own hands in a safe way, of course. But that's something that really inspires me and something that I would definitely look forward to do in the future. If I was to ever do research like that, it would probably be on developing some sort of application, something where you could, find where you're injured, find where, injury occurred in another person, and just like understand the treatment from there using AI software, modeling, machine learning, all that stuff.
Well, great. Thank you so much. We're going to move on to our next speaker, but if anyone has any questions for Matthew, please feel free to put them in the chat or follow up with him after. Matthew, you can drop your email, or you put your LinkedIn, but any other way you want people to contact you, you can drop it in the meeting chat as well.
Sounds good. I'll throw my email in. Thank you so much,
Okay.
everybody.